Good morning, all of you. Today we will see this chart, one chart concerned with the respiratory system, and this chart shows here the division of the lungs and the divisions of the bronchi and the bronchioles. And basically the most important part of this chart is these three graphs where you have this graph 1, 2 and 3. Okay, so what does this graph indicate and what are these lines? What are the significance of these lines? We will just discuss that in detail. Now, coming on to this slide here, it will somehow be like this. Now, this is the graph which is showing the pressure volume changes which are happening during each inspiratory cycle, during each respiratory cycle with respect to the changes in the volume which is happening in the lung. The second diagram shows the changes in the pulmonary pressure which is happening, and the third one is the changes in the pleural pressure. So what does this graph indicates? This graph indicates the changes which are happening within the lungs during each cycle of inspiration and expiration with respect to the changes in the volume, the changes in the alveolar pressure and the changes in the pleural pressure. Now to go back to our brief anatomy, we know that the breathing cycle per minute is somewhere around 12 to 16 to maximum 20 per minute. That is the respiratory rate. And during each breathing cycle, there is a phase of inspiration and there is a phase of expiration. The phase of inspiration is an active process where active energy muscles are used. The phase of expiration is a passive process where the passive process is because of the elastic recoil of the lungs and the relaxations of the muscles of respiration. And what is the main muscle of inspiration? The main muscle of inspiration would be the diaphragm, followed by the surrounding muscles, that is the intercostal muscles. Now, we know that this whole of these lungs are enclosed covered in a layer, and those are known as the pleural layers. We have got a parietal pleura and a visceral pleura. The gap between the parietal pleura and the visceral pleura is known as the pleural space, and the fluid present there is known as the pleural fluid. There is some pressure exerted in this pleural space, in this pleural fluid, and that pressure is known as the pleural pressure. The second thing is about the alveolar pressure. What do you mean by alveolar pressure? Now, the alveolar pressure is the pressure which is present within the alveoli during the inspiration and expiration. When you record the pressures, you will find that the pressures in the alveoli are changing during each inspiratory and expiratory cycle, and that record of the changes in the pressure which is during inspiration and expiration is depicted here. So ultimately, a change in the pleural pressure and the change in the alveolar pressure is also causing the air into the air entry and exit from the alveoli, and that is called as the volume changes, and that volume is the tidal volume. So what is the tidal volume? Tidal volume is the amount of air inspired and expired during each breathing cycle is known as the tidal volume. So now when we draw a graph here, initially this first half becomes the inspiration, the second half becomes the expiration, and now let's just correlate these three graphs. So first, what do we understand here? This is the beginning of inspiration. The whole inspiration process is reaching its peak. This marks the end of inspiration, and then there is a beginning of expiration, and this half marks the expiration. So this, from this point to this point, includes one inspiration and one expiration, and this is one breathing cycle. So this graph shows the changes of the air which is entering into the lungs during inspiration, and the amount of air which is leaving the alveoli during expiration. So these are the volume changes which are taking place during each respiratory cycle. Then now when we mark the pressure changes which are happening in the alveoli during the inspiration, the graph so what is depicted is like this. You see what is happening. This is the graph which is which is the graph which is recording the alveolar pressure. At the beginning of the inspiration, you will find that the alveolar pressure is falling down. It falls in the middle of the inspiration and then gradually increases, and it reaches a maximum there, which is the pre-inspiratory level, and during expiration it goes up and then again stays flat for some time and then reaches the pre-inspiratory level at the end of expiration. Similarly, we have got the pleural pressure here. When you see the pleural pressure, you will find that this is the pressure which is the recording of the pressure during inspiration. So initially during the inspiration, when it starts, you will find that the pleural pressure is falling. It remains at a little low level for some time. At the end of inspiration, the pleural pressure continues to rise, and during expiration it reaches a maximum to the pre-inspiration levels, and by the end of expiration it reaches the pre-inspiratory levels. So these are the three graphs. Now you have to correlate the whole of these three graphs. Before we correlate, I will just explain to you what is this happening here. Now we know that the lungs are enclosed in this pleural cavity and they are surrounded by the pleura and they are present in the thoracic cage. Now whenever there is an inspiration happening, the muscles of inspiration are taking part, the diaphragm is contracting, the intercostals are contracting, and because of the contractions of these inspiratory muscles, the thoracic cage is expanding. When the thoracic cage is expanding, it is pulling up the pleura along with it. It is pulling the parietal pleura along with it. So what is happening? There is because of the thoracic cage expansion, the pleural space is increasing and the pleural cavity is increasing. The pleural pressure is falling down. So the negative pressure in the pleura falls down. When there is a negative pressure in the pleura, it exerts this negative pressure on the alveoli which is surrounding it, and that exerts a negative pressure on the alveoli. So the alveolar smooth muscle wall stretches up, and this stretching of the alveoli increases the volume of the alveoli. When the volume of the alveoli is increased, the pressure in the alveoli falls. Now when the pressure in the alveoli falls below the atmospheric pressure, there is a gradient created from the atmospheric pressure to the alveolar pressure. So because of this positive gradient from the atmospheric pressure to the alveoli, there is a air entering from the atmosphere into the alveoli, and you will find that the lungs now begin to be filled with air, and that is why the volume increases there. So during inspiration, this is how the volume air enters into the alveoli, and the alveolar cavities are filled with air. Now at the end of inspiration, what happens? The muscles of inspiration stop contracting, they begin to relax. The thoracic cage is elastic in nature. The elastic stretch wall comes to an end, so they also recoil. When they recoil, what is happening? The diaphragm is pushed up, the intercostals are relaxed, the thoracic cavity is relaxed, as a result of which the diameters are reduced. When the diameters are reduced, the stretch on the pleura is reduced. When the stretch on the pleura is reduced, it causes less negative pressure in the pleural cavity. This negative pleural pressure in the pleural cavity exerts less negative pressure on the alveoli, as a result of which, because of this push from the pleural cavity, the alveolar pressure becomes positive and slightly rises above the atmospheric pressure. Because the volume reduces, the pressure increases. This is simple law of physics. So when the volume is reduced of the alveoli, the pressure increases, and this pressure increases above the atmospheric pressure. So now a pressure gradient is created from the alveoli to the atmosphere. So now we have more pressure on the alveoli, less on the atmospheric starch, comparatively less in the atmospheric pressure. So a gradient is created. When this gradient is created, air moves from the alveoli into the atmosphere, and this brings about the whole process of expiration. So this is how now we'll just correlate what is happening. At the beginning of the inspiration, here you will find that the pleural cavity is increasing because the pleural volume is increasing. The pressure in the pleura, which is somewhere around 0.4 or 0.5 mmHg, becomes more negative because of the stretch on the pleura. The pleural pressure falls to somewhere around -4, -5 to -8. At this point of time, because there is a fall in the pleural pressure, this negative pressure exerts a negative pressure or exerts a pull on the alveoli. The alveolar walls get stretched, when the walls get stretched, the alveolar pressure, which is somewhere at the level of the atmospheric pressure, let's say around 765 4 mmHg, that also falls down, and this alveolar pressure falls along with the pleural pressure. So there is a negative pressure exerted in the alveoli, so it becomes subatmospheric pressure. When it becomes subatmospheric pressure, the atmospheric pressure is around 764, here it is somewhere around 762 761. So a pressure gradient is created from the atmospheric pressure to the alveoli. So as a result of which difference in the pressure, air flows from a higher pressure to a lower pressure. So air enters into the alveoli. When the air enters into the alveoli, you see that the alveoli are filled with air, and this volume of the alveoli increases from nearly zero. It's not exactly zero, it would be somewhere around there, because some air is still left in the alveoli, so it rises up and reaches to around 500 ml. So this is the tidal volume here. So now at the end of inspiration, the lungs are full of air, the volume is around 500 ml, and you will find that the pleural pressure is somewhere around less than the atmospheric pressure, and the pleural pressure is somewhere around 0.8 mmHg. At this point, what happens is the inspiratory muscles stop contracting, they becomes relaxed. When they relax, the diaphragm moves up, the external intercostals recoil back, or they relax, the elastic recoil of the thoracic cartilage happens. Because of this, you will find that this recoil is now causing the pressures to rise. So now in the expiration, the intrapleural pressure from minus 8 mmHg begins to reach back to its original minus 6 and minus 4 mmHg, and along with it, because it is now increasing, the elastic recoil is not there, the negative pressure is not there, the alveoli also, or the stretch on the alveoli is reduced. So now they cause the alveoli are elastic, they also recoil. When they recoil, you will find that the pressure which was here subatmospheric or less than zero, now for a few seconds it goes above the atmospheric pressure. When it goes above the atmospheric pressure, that it becomes plus 1 or plus 2 mmHg, that is, it becomes around 768 769 mmHg. So now the alveolar pressure is high. When the alveolar pressure is higher than the atmospheric pressure, there is a pressure gradient from the alveoli to the atmosphere. Now air begins to move out from the alveoli into the lungs, and the amount of air in the alveoli begins to fall, and this is the phase of expiration. It continues to fall as long as this pressure gradient is there, and it reaches to somewhere around nearly zero level. This marks the end of the expiration, and this cycle goes on and on. So now this is how the breathing takes place. This is known as the pressure volume changes that takes place during breathing. To split it more, these are the pressure volume changes which are taking place during inspiration and during expiration. The gap or the difference in the pressure between the pulmonary pressure and the pleural pressure and the alveolar pressure is known as the transpulmonary pressure. So it is the transpulmonary pressure which is being exerted on the walls of the alveoli, which in fact causes the air entry into the lungs. Okay, now we'll complete with this slide. The next slide we'll go is we'll see about the lung volumes. The next slide we'll see is about the lung volumes. Yes. Now this has come a little twisted in a different angle. Now this is a chart which depicts the record of the various changes in the volumes which are happening during the inspiration, during the breathing cycle. Now if you see this, here we start 0, 1000, 2000, 3000, 4000, 5000 and 6000. This is the volume of the air which is entering into the lung, which is a record of the volume of the air, and here it is the time. The upper half gives the inspiration, the lower half depicts the expiration. Now remember 2-3 things here. First, 4 lung volumes are there, 4 lung capacities are there. If you understand the lung volumes, you can understand the capacities very easily. I will just briefly explain to you about what are the 4 volumes present here. So the 4 volumes are the tidal volume, the inspiratory reserve volume, the expiratory reserve volume, and the residual volume. So now just see this record here of the tidal volume. Now this is the record of the air which is entering into the lungs during each respiratory cycle. So what do you find here? The amount of air which is entering is called as the tidal volume. So this is the tidal volume, and it is the amount of air which is entering into the lungs is called as the tidal volume. The tidal volume is somewhere around 500 ml. This is the tidal volume which is happening, or which is around 500 ml during a normal resting breathing cycle. So it is the amount of air which is entering into the lungs at rest, and that is now called as tidal volume. The amount of air which is entering is somewhere around 500 ml. Now the next volume is the inspiratory reserve volume. Now inspiratory reserve volume is the volume of air which enters into the lungs on a forced inspiration after the tidal volume. So here you can see this is the tidal volume. What is tidal volume? The tidal volume is the amount of air which can enter into the lungs above the tidal volume on a deep inspiration. Say for example, if the person has breathed in air after normal inspiratory effort, you take a deep breath in, so the amount of air which is above the tidal volume which you can breathe in is called as the inspiratory reserve volume. And this inspiratory reserve volume is somewhere around 3.3 liters. See this is 3000 and this is 6000. So the gap is somewhere around 3 liters. It is around 3.3 liters. So what is inspiratory reserve volume? Inspiratory reserve volume is the amount of air which can be breathed in after a deep inspiration and above the tidal volume. It does not include the tidal volume. So this 3.53 liters does not include the tidal volume. That is above the normal air intake, the person has got the capacity to take around 3.3 liters of air more on deep inspiration. Then what is expiratory reserve volume? See, the word itself will say reserve means it's a reserve which is kept, which is the ability, and it can be utilized whenever there is a need. So now what is this expiratory reserve volume? Similarly, the expiratory reserve volume is the amount of air which can be breathed out on deep expiration after the normal breathing, that is after the tidal volume. See, it is from here to here is the expiratory reserve volume, and it is somewhere around 1.9 liters to 2 liters. So the expiratory reserve volume is the volume of air that a person can expire on deep expiration after the tidal volume or after the normal breathing. So this is around 1.9 liters. Next is the residual volume. What is residual volume? The residual volume is the extra amount of volume of air that a person can breathe out after the expiratory reserve volume is called as the reserve volume, residual volume. Then one capacity is the total lung capacity. The total lung capacity is the capacity of the lungs to the maximum amount which a person can breathe in air. So for example, the total lung capacity is from 0 to 6. So 6 liters is the total lung capacity in one respiratory cycle. This is from this end to this end, and that includes all your inspiratory reserve volume plus tidal volume plus expiratory reserve volume and the residual volume, and it is around 6 liters. So this is in as far as the formulas are concerned. But what does total lung capacity mean? The total lung capacity means the amount of air which a person can take air in, or the capacity of the lungs to accommodate the maximum amount of air is called as the total lung capacity. Lastly, there is one more capacity which I would like to discuss here is the vital capacity. Now, what is vital capacity? Now, vital capacity is the amount of air which a person can breathe out after a deep inspiration. So vital capacity is the amount of air which can be forcibly expired after a deep inspiration. So here you can see this is the vital capacity. So after a deep, this is a tidal volume, you have taken in 500 ml of air. Now take a deep breathe in air. So this is a total respiratory, inspiratory reserve volume. So after you have taken a deep breathe in, now you forcibly expire the air or exhale the air. So when you blow out the air, the amount of air which will be blown out or expired out gives the vital capacity. Now there are some factors here about the vital capacity. Now this vital capacity can vary with certain physiological and pathological parameters. So what is this physiological and pathological parameters? Now physiological parameters with vital capacity, the vital capacity is less in children, reaches a maximum in adults, and in old age it decreases. So first physiological variation is with age. Second physiological variation is with the sex of the person. In compared to males and females, you will find that the vital capacity is more in males than in compared with females. Then third, the vital capacity also changes during sleep. In sleep, to a slight extent, the vital capacity decreases. Then with posture, what happens to the vital capacity with change in posture? The maximum among the two things, lying down posture and standing posture, you will find that the vital capacity is maximum during standing position and slightly less during the lying down position. This is because of the position of the diaphragm. In standing position, the diaphragm is normally placed, so the lung capacity is increased. Whereas in lying down position, the diaphragm is little pushed up, so that the vital capacity is reduced in lying down position. Then in exercise, you will find that the vital capacity is increased. Now, the vital capacity is also decreased. It is decreased in certain lung diseases. We have got two types of lung diseases, restrictive lung diseases and obstructive lung diseases. So in these cases, you will find that the vital capacity is altered. When you come back to the college and we deal about the measurement of vital capacity, we will talk about the restrictive and the obstructive lung diseases. The word itself will suggest restrictive lung diseases means there is a restriction to the expansion of the alveoli. So if the alveoli are fibrosed or if they are damaged, then there will be restriction to the expansion of the alveoli, or if the chest wall is fibrosed or trauma to the chest wall, there is a restriction on the expansion of the chest wall or the alveoli, so that is called as restrictive lung diseases. Obstructive lung diseases is something where there is an obstruction to the flow of the air, either by means of the narrowing of the alveoli or some foreign body present, or there is a fluid which is surrounding there and leading to the obstruction, so it is called as an obstructive lung disease. Now there is one more term which is called as a timed vital capacity. Timed vital capacity means measurement of vital capacity with respect to time. So the amount of vital capacity in first second, third second, second second and third second will be altered. So that is called as timed vital capacity, TVC1, TVC2, TVC3, where what is the percentage of the vital capacity in the first second, second second and third second. What do you mean by this first second and third second? When you are blowing air out, if you remember the definition, the vital capacity is the amount of air which is blown out or expired forcibly after a deep inspiration. So this whole expiration takes place in 3 to 4 seconds because it's a passive process. So the amount of air which you are able to blow out in the first second is TVC1. That is the time vital capacity in the first second. Then the amount of air which you can blow out in the second second is time vital capacity 2, and it is in the third second. So there are certain proportions, standard measurements where in the first second a person is expected to blow 90% of the air which is expiring out. Second it reaches to around 95-96%, third it reaches to 19%. There are certain graded parameters. So if you are falling within those parameters on measurement, then you are considered as normal, or if you fail to match those standard protocol parameters, then there is a restrictive or a obstructive lung disease. This is about the timed vital capacity. This is another chart which is called as Systometrogram. Now, what is the Systometrogram? This Systometrogram is the measurement of the amount of pressure which is developed within the bladder, comparing that with the amount of the volume of urine present in the urinary bladder. So this is called as a Systometrogram. This Systometrogram is a record. On one axis you have got the volume of the bladder, and on the other hand you have got the pressure within the bladder. Now see this diagram. Let us understand this diagram, then I will briefly explain to you. This is the pressure within the bladder. This is the volume of urine present in the urinary bladder. So you will see that as initially the volume of the urine increases in the bladder, the pressure also slightly rises. So around 150 ml of urine till about 100 ml of urine, you will find that the pressure, there is a slight increase in the pressure within the bladder. Now subsequently, once the urine starts accumulating, say from 50 ml to around 400 ml, you will find that though there is a significant increase in the volume of urine within the bladder, but the pressure remains constant. There is no rise in the pressure and it's a plateau phase. Whereas once the pressure has increased, once the volume is increasing beyond 400 ml, you will find that the pressure within the bladder or the tension in the bladder wall increases significantly from somewhere around 10 mm of water to around 80 mm of water. So this graph has got three phases, phase 1A, phase 1B and phase 2. It indicates the amount of pressure which is built up in the bladder with the increase in the volume of urine there. So initially in 1A there is a slight increase in the pressure and a slight increase in volume. Then subsequently after that, any significant increase in the volume of the bladder does not changes the pressure within the bladder. At 400 ml, when the bladder is filled with 400 ml of urine, there is a significant increase in the tension wall or within the pressure in the bladder. So now what is the clinical significance? At 1A, when there is a pressure slight increase, you will feel that there is a bladder is full, and it will make you conscious of the fullness of the bladder, that you have to urinate. But with the rise in the volume, you are able to sustain it and there is no need or an urgency to empty the bladder. But once the volume of urine reaches around 400 ml, then there is a urgency or there is a need to void or need to empty the bladder. So this is the point where you are just conscious of the fact that the bladder is full, getting full, but at this point at 400 ml, at this point of time, you need to empty the bladder or void the bladder. So this is about the Systometrogram, the pressure volume changes, and this is explained by the Laplace law, where the Laplace law says that the pressure is directly dependent on the tension wall and inversely proportional to the volume. So this is how the Laplace law will explain these pressure volume changes, and basically it is meant to make you conscious at what level of urine present in the bladder there is a desire to empty or void. Now when you see the emptying of the bladder, you will find that the bladder is innervated. Urinary bladder is nothing but a thin detrusor muscle. This thin detrusor muscle contracts. When it contracts, it tries to expel its content out. The control is maintained by an internal urethral sphincter and an external urethral sphincter. The external urethral sphincter is controlled by some nerves and is under the cortical control, sensory nerves, and is in the cortical control, whereas the internal sphincter is purely under the parasympathetic supply. So whenever there is a parasympathetic stimulation to the bladder, two things will happen. The smooth muscle walls of the bladder will contract, whereas the sphincters will relax. So there is a contraction of the detrusor muscle along with the relaxation of the internal sphincter. Now once the internal sphincter relaxes, it gives you an urgency to void the bladder, and at that point the external sphincter also has to open up for the urine to pass out. if the external sphincter doesn't opens up, there will be a desire to empty the bladder, but it will be all under control. So once the external sphincter, that is the signals from the cortical areas are getting signals, the external sphincters will also relax, and then there will be voiding taking place. So what happens? What is the lesion here? What is the pathology here? So there may be a loss of control over the voiding of the bladder, which we call it as incontinence. So what is incontinence? Incontinence is the loss of ability to control the emptying of the bladder. That is incontinence. That may be two types: stress incontinence, where there is stress on the bladder, where you are coughing, pressure is increased. So whenever the pressure is increased, there is loosening up of the control of the sphincters, as a result of which even on coughing and laughing you will find that the urine is getting voided. Or there may be an overflow incontinence whenever there is a higher lesions of the higher centers. Whence the bladder, that is, I said, till 400 ml there is an urgency. Beyond 400 ml there cannot be a control. So whenever the bladder volume is increasing beyond 400 ml, the urine is flowing out. Then there will be an urgency incontinence, where in urgency incontinence normally the detrusor muscle is contracting, the internal sphincter is relaxing, but till there is a comfortable place to empty the bladder, the external sphincter remains contracted. In urgency incontinence, the external sphincter does not contract and open out, so there is an immediate voiding taking place. So that is called as urgency incontinence. So basically, there can be lesions at two places. Damage to the sensory nerves of the bladder can lead to incontinence. Damage to the sensory nerves and the motor nerves can lead to incontinence, bladder abnormalities, or damage at the higher level cortical centers can also lead to loss of bladder control. So three places you can find the lesions. One, the sensory nerves getting affected. Second, the motor nerve, that is, the motor means the sympathetic nerves getting affected. And thirdly, any lesion at the higher center will also cause to the incontinence of bladder abnormalities. So this is about the Systomic Program. The next slide, this is a very simple slide. Quite a lot is being given in your textbooks. I will just explain to you one thing. This is about short-sightedness and long-sightedness. There basically you can see one thing only happens. Here either the image is formed in front of the lens or the image is formed beyond the lens. So there is resulting in a myopia and hypermetropia, commonly known as short-sightedness and far-sightedness. Now basically at your level you have to remember why this is happening. Why is the image either getting formed in front of the retina or it is forming behind the lens? Not in front of the retina, in front of the lens or beyond the lens. So there can be 2-3 abnormalities which you should remember. Now normally there is a anterior-posterior length of the eyeball. If there is a change in the anterior-posterior length of the eyeball, then the image can either fall in front or it can fall behind. So the first parameter or the first etiology or the first cause for this refractive errors could be either an increase in the anterior-posterior length of the eyeball. So because the length of the eyeball itself is increased, the image is forming in front of it. Or it could be shortening of the anterior-posterior length of the eyeball. So a short anterior-posterior length of the eyeball will cause the image to form beyond the lens. So one of the one of the reason is change in the anterior-posterior length of the eyeball. The second could be there should be a change in the refractive index of the conducting system of the liquids present there. So if there is any change in the refractive index of the aqueous humor of the fluids present there, you will find that because of the change in the refractive index, the image can form in front or image can form beyond the lens. Secondly, the third is the change in the curvature. The change in the curvature of the cornea, the change in the curvature of the lens can result in the image being formed instead of on the retina, in front of the retina or behind the retina. So you remember these three things. One, change in the anterior posterior length of the eyeball, change in the refractive index of the medium through which the light is passing in the eye. Third, it is the change in the anterior, change in the curvature of the cornea or the lens, which will cause the refractive errors of the eyeball. Now, what is the farsightedness and what is the correction, that all you will find it in the books. I think with this we will stop for the day. The next class we will see and discuss some revision topics. Some of your students in the mail have sent that they want some revision of some topics, which we will start from the next class. Some more charts, I'll just show it to you here. I think they have already been discussed. This is about the oxygen hemoglobin dissociation curve. You know that this is plotted around the amount of oxygen present and the pressure present here. So this is the saturation levels and this is the amount of oxygen percentage present. Normally it is a S-shaped curve. This is a S-shaped curve. When you are discussing about this S-shaped curve, you have to discuss why is the plateau present here and why is the steep fall here. So this plateau indicates that any increase in the pressure from 60 mmHg to 100 mmHg volume of oxygen, the oxygen saturation doesn't improve. Whereas then there will be a shift of the curve to the left and shift of the curve to the right. What are the causes of the shift of the curve to the left and what are the causes of the shift to the right? You have to read them, and then you also have to know about what is Bohr's effect and what is Haldane's effect here. Specifically in oxygen dissociation, oxygen hemoglobin dissociation curve, you have to remember about the Bohr's curve, Bohr's law. Okay, with this we stop, and with this also we complete all the charts which we had planned to be the exam charts. We finished the non-endocrine portion. The endocrine portion is completed already in the month of January or February. From the next class we will discuss about some revision topics. Thank you one and all. Have a nice day.